Because technically you cannot go faster than the speed of light, but space can travel faster than the speed of light. That's what's meant by warp drive.
NASA has been launching space probes and telescopes for a long time, but none is as impressive as the James Webb Space Telescope. Despite its high cost and long delays, no other telescope has generated such high hopes. But now, the new powerful telescope has made a startling finding about something called a warp bubble, which could have major implications. What exactly is a warp bubble? What did the JWST discover? And why do we need to be afraid? Let's delve into this discovery that has left scientists scratching their heads.
As far as we know, nothing can travel faster than the speed of light in a vacuum, period. It's not like we haven't wanted to make that happen. It's not like we haven't looked around the universe to see if we can find something that violates that rule. We have. We've looked hard. We've never found anything to violate that rule. Not only that, it is a fundamental tenet to Einstein's theories of relativity. So what that says is this speed of light rule is not a limitation of technology. It's a basic fundamental feature of the universe. Now, there are other ways to go faster than light. You can cheat in a legal way. For example, on Star Trek, what did they have? They had warp drives. Warp drives, what did that do? Well, here's your galaxy, and they're on one side of the galaxy and they want to get to the other. So what do? They turn on the warp drive, and that takes the space-time continuum and bends it. And now here's where they are, and here's where they want to go. They just take a little gap through the fabric of space-time, unwarp the galaxy, and there they are. They cross the 100,000 light-year diameter galaxy. Works every time. So that's legitimate in the sense that we know space and time can curve. And if you can control that curvature, you can get to a place much faster than a light beam would have taken. Much less time than it would have taken a light beam to traverse that same journey. I want warp drives that can do that. That would be really cool. But not only that, this little path that they took to cut from one part of their space-time to another, we have a term for that as well. It's called a wormhole. That is a portal in the space-time continuum that takes you from one part of the universe to another. And the more energy you have, the more you can curve major sections of the universe to traverse great distances. And I assert that if we're ever going to travel the stars, if we're ever going to cross the galaxy or visit another galaxy, it's going to have to be in some kind of way that exploits wormholes and the curving of the fabric of space and time. It's going to have to, because our fastest spaceships, if you hop a ride on them today, would take you 50,000 years to reach the nearest star to the sun. And the nearest star to the sun is sitting on our nose compared with the scale of the galaxy.
Space is a vast place with many interesting locations to explore. There are countless stars, galaxies, exoplanets, black holes, and much more out there. Humans, as a species, are naturally curious and want to understand their surroundings, both nearby and far away. Because of this, we're curious about what we can discover out there. Could there be cosmic neighbors as intelligent as or more intelligent than Howard's? Is there any exoplanet out there that could support life in some way? However, one challenge for space exploration is the great distance involved. Virtually every corner of the universe is incredibly far away. If you were to ask Elon Musk, who aims to establish a human presence on Mars, our neighboring red planet is relatively close. Given the immense size of the universe, volunteers for Musk's colonization effort must endure over 5 months of travel through deep space's harsh conditions before reaching their new home. But what if you're interested in visiting the nearest exoplanet to Earth, Proxima b? Achieving that dream is currently beyond the capabilities of modern technology. This exoplanet is located 4.24 light-years away. A light-year is about 5.88 trillion miles, making the nearest exoplanet's distance approximately 25 trillion miles. Unfortunately, that's just not a realistic possibility.
We can travel to the moon, it's like 3 days. Mars is 9 months, some other planets, a year, 2 years, 5 years, and we could probably get to the outer solar system in 10 years. That's within a human life expectancy. But here's my point. Until we discover wormholes or warp drives or something that could greatly shorten the time it takes to travel the vast distances of interstellar space, journeys across the galaxy will be hopeless unless we take on a different understanding of space travel and say, here's what we're going to do.
Nevertheless, our curiosity for exploration remains unbroken, and we found a way to observe distant celestial objects, space telescopes. If we can't reach these objects, we can deploy powerful telescopes to study and uncover their mysteries from afar. Galileo was the first to direct a telescope at the sky for cosmic discoveries. However, the sophistication of modern orbiting telescopes would likely surprise even Galileo. NASA has a long history of launching telescopes into space. Among the most renowned space telescopes is the Hubble, which has provided valuable insights for many years. Positioned in Earth's orbit, the Hubble is directed by scientists toward different parts of the universe. Yet, NASA continues to launch satellites and find new uses for them. Concerning the warp drive, a new space eye now surpasses any previous tool for observing distant universe objects. This is the James Webb Space Telescope, which takes the lead from the Hubble. The fact that it has surpassed the Hubble speaks to its exceptional nature. In terms of power, the JWST is 100 times more capable than the Hubble. Currently, the James Webb Telescope can observe the universe's history up to about 330 million years after the Big Bang. Thanks to the JWST, scientists can now peer even further back in time to witness stars forming close to the universe's birth event. The JWST can look back billions of years because light from distant stars has finally reached us after traveling for billions of years across trillions of miles. This light will provide insights into what those stars looked like in the past, even if some have since died. After being shrouded in secrecy, NASA has unveiled the initial set of images to showcase the JWST's capabilities. The collection includes images of nebulae and radiant regions in interstellar space, including the Carina Nebula. Situated approximately 7,600 light-years away, the Carina Nebula is a cloud of gas and dust hosting bright stars much larger than our Sun. The Stevens Quintet, a cluster of galaxies roughly 1 million light-years distant, will also be featured in the images. This galaxy group is intriguing due to 4 out of 5 galaxies engaged in a gravitational dance, distorting each other's shapes. We'll also be treated to the stunning images of the SMACS 0723 galaxy cluster. This cluster's galaxies bend and magnify light from objects behind them, allowing telescopes to detect faint, distant galaxies. This is where the JWST truly shines. This scenario is where the JWST performs exceptionally well. Lastly, initial images will include WASP 96b, a massive exoplanet orbiting a star 1,150 light-years away. Technically, the JWST won't produce an image of the exoplanet, but will provide a spectrum instead. The spectrum reveals the molecules present in the exoplanet's atmosphere, a crucial aspect of astronomy. This is an area where scientists are excited to utilize the JWST's capabilities. Discovering exoplanets is challenging due to their interactions with the stars they orbit. However, the new telescope is expected to simplify this task. Scientists aren't merely searching for exoplanets, they're studying them to uncover signs of life. The JWST might be the space telescope that ultimately detects extraterrestrial life. Nonetheless, few JWST discoveries will rival the warp drive's potential impact, as it could revolutionize space travel. Let's begin with an explanation of a warp bubble. This is quite a complex topic that requires advanced math knowledge for a thorough understanding, but we can provide a basic description. A warp bubble is a region of space that contracts at the front and expands at the back. The expansion and contraction theoretically propel the bubble and its contents forward at speeds exceeding light, all while following the laws of physics. When you travel in a warp bubble, you're not technically exceeding the speed of light, you're riding within a condensed space bubble. The excitement around warp bubbles is due to their ability to solve a major challenge of faster-than-light travel: time dilation. How does this work? Suppose you somehow manage to travel faster than light. Everything outside your craft would speed up, potentially translating a 3-hour journey to a beautiful tropical planet into years passing on Earth. In simpler terms, if you intend to travel faster than light while adhering to known physics, you might have to say farewell to your loved ones before embarking on your journey. However, warp bubbles avoid this problem by maintaining the unaffected space within the bubble. Thus, an hour of travel within a warp bubble would only account for an hour passing for those outside the bubble. This characteristic of warp travel is familiar to fans of the Star Trek series. Warp travel is a concept from the Star Trek universe, featured in numerous television series and films since its inception in 1966. Characters in these movies explore the cosmos using speedy spaceships and interact with various alien species. The torsion engine is the main focus, since the story wouldn't make sense without it. The universe is vast and peculiar, especially if you're thinking of reaching the next star. The enormous cosmic distances create an almost impossible obstacle. Let's consider the next star, Proxima Centauri, which is 4.5 light-years away. This gap means it takes 4.5 years to reach the star, even if you could travel at the speed of light. Light travels at the fastest cosmic pace and acts as a sort of universal speed limit, making other methods slower. Using the fastest space probe, the Parker Solar Probe, the journey through interstellar space would take nearly 8,000 years, so it's more reasonable to stay on Earth and its nearby surroundings. The Star Trek crew ventured far from Earth due to a solution they found. This solution enables long-distance travel by reducing the distance using the torsion engine's warp drive, providing great entertainment. Warp drive was thought to be fictional until a scientist realized its potential at the end of the last century. Warp bubbles remained in the realm of science fiction until theoretical physicist Miguel Alcubiere introduced his warp drive concept in 1994. This maintained Einstein's general relativity while establishing faster-than-light travel. Miguel Alcubiere was a physicist behind this groundbreaking theory. In 1994, while researching Einstein's general theory of relativity, Alcubierre was inspired after watching an episode of Next Generation. Alcubierre's calculations led to an article in Science magazine that same year. Alcubierre's paper explains how to compress space and time in front of a spacecraft and expand it behind, creating a torsion bubble. This means traveling a shorter distance to the destination within the torsion bubble. The visualization is akin to a surfer riding a wave, a metaphor often used to explain star travel. However, a challenge arises with Alcubierre's warp bubble. The warp engine is hard to construct in reality. You can't curve space forcefully with regular mass. Exotic matter with negative gravity is needed for this purpose. Alcubierre's warp drive involves creating a bubble of flat spacetime around the spaceship and curving spacetime around it to shorten distances. This requires either negative mass or negative energy density, but the latter seems more likely. Since negative matter hasn't been observed, negative energy is the only option. To generate negative energy, a warp drive would use a large amount of mass to create an imbalance between particles and antiparticles. For instance, if an electron and an anti-electron appear near the warp drive, one of the particles gets trapped, leading into an imbalance and negative energy density. Negative energy is used in Alcubierre's warp drive to form the spacetime bubble. However, generating enough negative energy for a warp drive requires a significant amount of matter. Alcubierre estimated that a warp drive with a 100-meter bubble would need the mass of the entire visible universe. This seems impractical. Nonetheless, physicist Chris van der Broek showed in 1999 that expanding the bubble's volume while keeping the surface area constant would reduce energy requirements to about the mass of the Sun. This is a substantial reduction, but obtaining the mass of the Sun for a single trip remains a challenge. Many warp engine publications followed over the years, but they all remain theoretical exercises exploring the theory of relativity for insights. The need for exotic matter persisted. That changed when physicist Eric Lentz began researching the concept. Lentz watched Star Trek as a child and couldn't let go of the idea of a warp drive. Lentz first encountered Alcubiere's article as a teenager and continued reading warp drive publications as a physicist. During the COVID lockdown, he revisited his old interests. This is when he noticed something overlooked in the article. Alcubierre explored the simplest solution to relativity's formulations, leading to the Alcubierre engine, a warp bubble powered by negative gravity. Lentz decided to explore unusual mathematics and found practical solutions. In Lentz's torsion bubble, mass was concentrated where curvature was highest, and the bubble could be created with everyday materials. Stranger things weren't necessary. Lentz was surprised no one had tried this before. Lentz's engine was more practical than Alcubierre's, though a significant amount of mass was still required. But it was a manageable amount. Warp bubbles seemed less impossible as a concept. There's still a substantial mass requirement, though it's more reasonable. Yet a lot of mass is needed. However, a serendipitous discovery is reigniting interest in warp bubbles and could be a breakthrough. For warp drive enthusiasts, another source of hope emerges. The accidental discovery method might lead to constructing a functional warp drive. Harold White, sponsored by DARPA, is working on a project related to this. White and his team shared their work on the energy distribution in a Casimir cavity from the Eagles Works laboratory. Their report shows a micro-nanoscale system accidentally predicted the distribution of negative energy density needed for Alcubierre's concept. In essence, they created a microscopic experiment while studying energy distribution around wavelengths, a theory developed by physicist Hendrik Casimir. The result matched Alcubierre's warp speed theory. White explained that their Casimir cavities analysis led them to a manufacturable nanomicrostructure that could generate negative vacuum energy density, creating a genuine nanoscale warp bubble. These specific conditions could manifest a true warp bubble structure. White also knew about Alcubierre's mathematically valid idea for a warp drive that could travel faster than light without breaking the laws of physics. He was aware of how the solution had been criticized for using theoretical materials and huge amounts of energy that seemed almost impossible to create practically. While working at NASA's Eagle Works laboratory, White, a warp drive specialist, adapted Alcubierre's original idea into a simpler form. This new design greatly reduced the need for exotic materials and energy. The revised concept gave researchers and sci-fi enthusiasts a glimmer of hope that a real warp drive could exist one day. This led to the informal renaming of the original concept as the Alcubierre White Warp Drive. During his DARPA-funded research on Casimir cavities, White unexpectedly stumbled upon a discovery supporting a theoretical concept he often spoke about. Casimir cavities and quantum-scale forces weren't previously linked to warp drive theory. White and his LSI team were enthusiastic about this work, which DARPA believed had various potential applications. Coincidentally, or fatefully, one of the few engineers who could recognize the similarity between this Casimir cavity research and his warp drive passion was in the right place at the right time. White's team published the first peer-reviewed paper proposing a feasible nanostructure for a warp bubble. This fortunate finding confirmed that predicted structure and energy aspects of a warp bubble, providing guidance for future research. According to White, we suggest a potential structure that could generate the required energy distribution for an Alcubierre space warp. To progress the research, White's team proposed a design for a testable nanoscale warp drive craft. The initial experiment involved a toy model with a small sphere inside a cylinder, showing energy density matching warp metric requirements. This analysis revealed a three-dimensional energy density linked to the Alcubierre warp. White believes chip-scale experiments could detect small signs of theorized phenomenon, a real warp bubble. As a Star Trek enthusiast, White encourages using this structure to generate energy density for a warp drive. While they haven't built or tested the nanoscale warp craft, they could use a Nanoscribe GT3D printer. They have the means, They just need the opportunity. White's team is currently focused on Casimir cavities with no plans for the warp craft. Though they couldn't build the nanoscale warp craft, they proposed a chain-like experiment with multiple Casimir-created warp bubbles. This configuration would help us understand warp bubble physics and potential space travel. White hesitates to create nanoscale warp drive models. DARPA funds LSI EagleWorks for Casimir cavity exploration, not accidental warp bubble discovery. White anticipates designing and testing the mini-warp craft, whether by him or another researcher. He cautions that building a functional warp drive requires more scientific progress. While it's not imminent, there's hope that humanity could one day explore the cosmos using a Star Trek-like warp bubble. While White's work on Casimir cavities had originally veered away from the realm of warp drives, it unexpectedly intersected with his passion project. The Casimir Effect, a phenomenon in quantum physics, involves the attractive force between two closely placed uncharged conductive plates due to fluctuations in the quantum vacuum. This effect, while seemingly unrelated, held the key to a potential breakthrough in warp drive technology. As White delved deeper into his Casimir cavity research, he found that the energy density distributions produced by these microscale structures bore striking similarities to the theoretical requirements of the Alcubiere warp drive. The discovery was met with excitement and a sense of serendipity, as it offered a bridge between two seemingly disparate areas of study. However, White remained cautious. He recognized that the path from the unexpected discovery to a functional warp drive was still fraught with challenges. The Casimir Effect, while intriguing, had its own set of intricacies that needed to be thoroughly understood. The prospect of harnessing this quantum phenomenon to create a warp bubble capable of bending space-time was a tantalizing one, but it required careful scientific scrutiny. White's proposed design for a nanoscale warp drive craft was a leap toward practical experimentation. It envisioned the creation of a structure that, when manipulated with precision, could initiate and control a localized warp bubble. The implications were profound. A successful test could signify the first steps towards a real-world warp-capable spacecraft. This was uncharted territory, where science fiction's wildest dreams emerged with the rigor of scientific investigation. Despite the excitement, the challenges remained formidable. The energy requirements, the intricacies of manipulating quantum forces, and the need for precise engineering all demanded concerted effort. White's belief in the potential of a warp drive was unwavering, but he remained grounded in the realities of scientific progress. The Casimir cavity experiment provided a promising avenue, but it was just a piece of a complex puzzle. As White and his team pressed forward, they sparked curiosity across the scientific community. The journey toward a realizable warp drive had captivated the imagination of researchers, aspiring to make the impossible possible. The potential for interstellar travel, once relegated to the realm of science fiction, was now a subject of legitimate scientific exploration. So thanks for joining us today. If you enjoyed watching this video, give it a thumbs up, and don't forget to share your thoughts in the comment section below this video. We'll be back with another amazing video. Until then, goodbye and peace.